It's a great pleasure to have Claire Foster here, the new lecturer for this year. New to the course, but certainly not new to Julia. I think that without Claire Foster, I would know nothing about Julia. She brought Julia over to Brisbane in 2000.
Oh,
Oh, you have my
arguably.
2013 or 14?
I don't know. I don't even know. Yes, it would have been sometime like that.
Sometime in the previous decade.
I don't know the answer to that.
Yeah, and truly a Julia expert, contributing to the, not just to packages, which is already a thing, but actually to the actual Julia infrastructure core. And I'm sure you'll hear about that from Claire as you get to know her more during the lectures. So there's now a quick unit, which is really about the heart of well, you called it the nouns and verbs of programming through the Julia language. That's this quick unit. Obviously, people here, people at home, you have big homework on your mind, but I hope that this lecture, this hour today, and then the 2 hours next week after big homework and just prior to the quiz can actually enrich you. This material is not quizable, but it will be important for project number 1 that will come straight after. And yeah, truly a great pleasure to have you, Claire. So can we acknowledge Claire first lecture of this year? Thank you.
Thank you.
Enjoy.
Okay, yeah, let's get started. So I'll just look super quick about me. Maybe we'll talk a little bit more about things I've done later, but thanks, Ernie. I was trained as a physicist here at UQ. I did my PhD in physics over on that side of the big quadrangle, whatever. Yeah, and then I kind of got a bit sick of the academia side of things and wanted to make things that worked in the real world, I guess. So, and I really liked software, and I kind of discovered that as part, like during my studies, I guess. So I kind of went and worked in technical computing things. And when I say that, I sort of mean like the intersection of programming and mathematics, statistics, and science, I suppose. So I worked in mapping. You've probably, which is where I've met the other lecturer, the previous lecturer, Paul. And I worked in MRI for a little while as well. So medical research and imaging, spectroscopy. Yeah, and then I kind of wrote so much package code and Julia code in the core of Julia that I decided I wanted to work on Julia itself. So now I work on the Julia compiler. I work with the people at Julia Computing on the Julia compiler. So yeah, that's lots of fun. And we could talk more of that later, maybe. So yeah, I'm working to replace the front end of the compiler and make the error messages better and stuff like that. Okay, but yeah, so onto this unit. So this unit is just going to be it's kind of a tour, I guess, of a whole pile of language features that Julia has for kind of software architecture, I guess, designing your software, making it easy to write, making it easy to read, those kinds of things. So there's lots of sort of desirable properties you might want in a programming language. And if you wrote these notes, I haven't modified these notes, so I'm just going to like slightly disagree with him on some things, but they're wonderful notes. Some of the things that you might want in a programming language are things like execution speed. So you want the code to actually run fast so that you can get your answers quickly. You might want it to be easy to write the code. So, and you should be like, it should be expressive. You should be able to write a small amount of code to achieve a lot of functionality, I guess. And one thing which might not be obvious if you haven't worked in sort of large software teams or anything is that you want the resulting code to like enable scalable engineering, is what Andy's called it here. So when you have a big team, you want to be able to have everybody on the team understand and work on that code. And what often ends up happening is once the system gets big, it can be just really difficult to understand the code that's there for new people or for existing people. yeah, you get stuck in like a tar pit of complexity. People get worried about changing the code. People don't understand the code. So what you want in a language, one of the things that you want is you want it to be easy to read those and understand those large pieces of software as a team, so that you can actually just continue to develop the thing. So those are some things that you might want in a programming language. I think there's more things that you could want. So other languages make different choices about what they emphasize, I suppose. Like, for instance, you might want to have a high confidence that your programs are correct. And so sort of system programming languages like Rust go to great lengths to ensure certain types of correctness, and the compiler might be able to prove that that certain things can't happen in your program. So that's really good. Julia is not like really focused on those problems. We get some benefits from our type system, but less so than something like Rust, which you can really have certain types of proofs in the type system that things will be correct. Anyway, but back to Julia. See, it's a high performance language for mathematical problems. So we kind of emphasized those things that Andy's written there. So you want to, it needs to be able to be fast, and you want to be very expressive in a mathematical sense. So like you want your code to look like mathematics in a sense. And yeah, I've already sort of talked about scalable, I guess, like software teams and scalable coding in some sense. But yeah, Julia is very good at allowing you to take different modules, like different packages written by different authors, and to use those together in a way that like they all kind of work together elegantly. So yeah, it's very good at that. Yeah, so okay, the like kind of goal of this unit is to kind of give you a bit of a tour of various Julia language features, which show you how to kind of use these features, or show you how to use these features to kind of build programs. Okay. So need time. Okay, there we go. Yeah, so in Julia, we sort of emphasize values and types a lot. So all valid Julia code is an expression. That means that it produces a value. It's not like some languages where there's statements which don't produce, like they don't produce a value, not something that you can assign to. Things like C have void, for instance. So in Julia, every expression that you can write has value. Every value has a concrete type, and even functions as well are values. They're first class in a sense. So they can be passed around and passed to other functions. That can be extremely useful. So if you have anyone's used do blocks, you'll know about that. Yes, and we're going to get to that in just a minute. That's a tricky one, though. Okay, so why is it so? Why do we have types? I'm not sure I had much to say about that section. Oh no, yeah. So okay, so yeah, so values have types, and types are really important for kind of two major reasons. I guess we've got listed here. So for the human type, we can use types to like define our data. So we need to model our data where kind of which is flowing through our program. And if you want to know something about that data, you can go and look at the type of that data and see the properties of it and understand what it's for. And we can use the types as well that we define to specify which functions can act on particular types. So I guess like that in terms of modeling like your program, you've kind of got nouns and verbs. You've got your types, which are the nouns, and you've got your verbs, which are your functions. And finding the right nouns and verbs is kind of like one of the key parts of like designing your program in a way that's like kind of comprehensible. So that's like one reason. It's for the humans to sort of write abstractions and make like expressive code. And the other reason is to let the compiler know about how the types might be, or how things are represented in memory. So if we want to generate really efficient code, we need to have a like concrete representation in terms of bits of what our data is, and the compiler needs to know about that. Okay, so let's get onto some actual code. Okay, so great question about print line. So here's some expressions. It's not very exciting. We've got an integer, an array, and we've got this one here, which is a bit curious. So let's talk about that one. So because all expressions are yield a value, we can assign X, Y, and Z to those things. Okay. So yeah, if we look at the types of those, well, we'd find that this one is just an integer. The type of this array, Y is a vector of string. So it's just an array, a one-dimensional array with strings in it. And the last one's the interesting one. So the type of Z is nothing. So when the function of println is really to have a side effect. So we will print that to the terminal. And like imagine like plotting, that's another example. Like the function of a plotting thing is to have a side effect, which is to show something on the screen. There might not be a useful value. Well, there could be, it depends how it's set up, but there might not be a useful value that can be produced from that. It's really having a side effect elsewhere in the system, which is the point. So yeah, in the case of println, that's the case. So it just returns nothing instead of, like, there's no value to really return. It returns this thing called nothing. So we can type nothing if we want to. So there's a special rule in the Julia REPL, is that the value nothing is never displayed. So we could go show nothing, I guess. Actually, I don't know what that's going to do. Okay, yeah, so shows that it's actually nothing. So the nothing, lowercase nothing versus uppercase nothing. So the type versus the value. So the type of nothing is that one. Yeah. Type of nothing. Oh, that's a data type. There you go. So types also have types. Everything is a value and everything has a type. Even types have a type, which is data type. Okay.
Abstract types.
Sorry?
Does that include abstract types?
Yeah, okay, so we can do type of union. We'll see union in a minute. Like a bool and a string. Yeah, oh, this is going to be something funny. Oh, no, it's not actually funny. It's just a union. But yeah, so unions have a type. This is not displaying all the details of what's in that union. It's just showing what the type is. Yeah, so, and you can have, everything has a type. That's a funny one. Play with that one later if you want. I won't digress too much to talk about unional. Okay. Oh yeah, so we've talked about nothing, that's fine. Okay, so what about concrete types? So every value has a concrete type, not an abstract type like this union, it's a concrete type. So you can think of a type as a set of values. So the type bool has only two values, just true and false. The type int64, which is 64 bits, has 2 to the 64 possible values. So it's a set, you can think of it as a set with 2 to the 64 values. All right, so every value has a concrete type, like that being like its actual, concrete, meaning that like you have to represent that value concretely within the runtime. And there's just these concrete types. I think I would arguably say that tuples should be separate here. Andy's grouped it with struct. So we have primitive types, which we'll talk about in a tick. We'll talk about all of these in a minute. We have struct, mutable struct. We have tuples. We have arrays. And we have string, which is a bit of a special kind of array almost. Now, yeah, so actually in Julia 1.11, these are no longer primitives. These are actually just structs, and there's a new primitive type called memory. So it's even simpler than before. Yes? Sorry, there's a concrete type. It partitions a set of values. Oh, okay, yeah, I guess you could think of it that way, yeah. Like, I mean, if you think of the set of all values that you could represent, that's like the any type, I suppose. Any is like like the parent type of all types, all possible types. Yeah. So no, it's an abstract type. Yeah. Yes. Okay. We'll look at like the hierarchy of types later on. These types, yeah, you can have types which are super types of others. Anyway, we'll look at the hierarchy of types later. So primitive types are a bit of a, are we doing for time? Yeah. Primitive types are a bit of an oddity. You won't use these yourself, most likely. They're the kind of thing that I've only written a handful of times, and I've written quite a bit of Julia code at this point. But yeah, so primitive types are just a box of bits. And you need these because you need like some way of saying to the compiler, or just like representing the most basic things, I guess, to the compiler. So a primitive type like this one, so saying there's 8 bits. So there's 256 possible values for this thing, which we've called uint64, unsigned 8-bit integer. So we could make our own one of those. There's really not much we can do with that at the moment. The compiler doesn't know. Doesn't really know what that thing is. It doesn't have any behavior, but it does know that it has 8 bits. That's about all it knows about it. Yeah, so the definitions of int64 and float64 in the Julia compiler look roughly like this if you were to write them in Julia code. I kind of lie because, I mean, they're not, the runtime needs to bootstrap itself. So technically this is not defined in Julia, but this one I think is actually. But it could be if bootstrapping was easier. Yeah, so so each of those types have 2 to the 64 possible values, and they are distinct from each other in the sense that like a float64 is not considered exactly the same as an integer, which is also 0. So like we have 0 equals 0.0. But if you look at exact equality in terms of their type as well as their value, then they're not the same thing. So we could look at, I mean, and each one of those is, as I said, it's a box of bits. So we can look at the bits if we want to. So if you reinterpreted like the float 1.0 as a uint64, you can have a look at all the bits there in hex. You've seen hex representation already, right? Yeah, okay, cool. So yeah, so you can see which bits are set for that. And that is a different thing actually from the int one, which is a lot simpler. Okay. Yeah, so there's just a little note here that the type tracking occurs at compile time usually. So even though everything has a value, or all values have a type, and it's very dynamic, you can see that we can define these things in the REPL and like play with them. Normally the compiler will do type inference and then use the values, like the types which have been inferred, to generate really efficient code. And okay, so there's a little note here as well about these types, just the fact that int and float64 are different, even if they have the same bit pattern. And like we were talking before about, like you've got to decide what the verbs are in your program. So the plus verb, you have to, like at some point you have to tell it what's it mean to add 2 integers and add 2 floats, and those have different bit patterns. You need to implement them differently. There's some different CPU intrinsic that will be called for those. So yeah, specifying the type when you define these functions plus is the way that we like tell the compiler what to do with add 2 integers versus adding 2 floats. So you can tell it the difference. Like, please use this one for floats, please use that one for integers. So we'll get on to dispatch later. That's like, which function do you choose? But that's like pretty critical thing. Yeah, primitive types are all immutable. You can't change the value of, if you've got x equals 0, you can't kind of somehow set the value of x to be something else. That doesn't make sense. That's not even a function, but you just create a new one. Yes. You can't make false true. No, you can't make false true. Yes. So false is a literal value. It's not a constant set to something. It's not an false is not identifier. It's a literal. It's a Boolean. So like it's not like my false. So I think there's other languages where that can be done. Is there? Python maybe, or JavaScript. I think maybe JavaScript. Like usually these bad things can be done in JavaScript. Yeah. So you can get into all sorts of trouble. You can do other things which will break your Julia session, like override the definition of plus for integers. So let's just do that because it's funny. I'll probably have to restart in a minute. So base.plus of like I is an int64. Or we'll just use int, which is an alias for int64. And equals hi. No, let's go surprise. I'm not sure what's going to happen here. Oh, yeah. Okay, yeah. Julia immediately crashes. So basically, yeah, if you try and say that plus of 2 integers equals a string, then yeah, everything explodes. Yeah, for understandable reasons, because adding 2 integers is like a pretty important operation in the runtime. Anyway, yeah, no surprises there. Okay. Structs. Okay, so like enough about primitive types. Those are pretty niche, but they're kind of just what is kind of underlying like a lot of the other types that you'll build. So structs allow us to organize data to various different types of data together into an aggregate. So one example is this little complex number here. I might use my in front of that. So like a lot of these things, complex 64 doesn't exist, but complex without the 64 exists in the runtime already. And I'd rather not just override what is built into Julia, because things can go funny. So anyway, we have my complex 64. So that's a struct, and it has a real and imaginary part, and we can make one of those things. So the name of that type acts as a constructor. So it's a function you can call, and you put in the values of the fields, and you make one of these things. So this doesn't have any behavior at the moment. The runtime does know how to print a value of my complex 64 in some kind of generic way, but it doesn't know that it's really meant to be a complex number. We would have to define a whole bunch of functions if we wanted it to know that. So yeah, it's not going to print nicely like this one, the built-in complex value will. So, okay, yeah, so with this struct here, the compiler knows that it's made of 2 float 64s. And so it's going to be, when it stores one of these things, it knows it needs 128 bits to represent it, and it will store it compactly. So if you have an array of these, for instance, this will be stored like as the real amount, the imaginary part of the first one, then the real part of the second one, the imaginary part of the second one. So like that's how it's laid out in memory, and that's very efficient. Yeah, what else have we got here? Okay, so yeah, we can, okay. So if we have one of these structs, Z equals that, then we can get access to the components of that. Yeah, with the dot syntax. So yeah, that's like pretty standard aggregate type. Most languages have something along these lines, or many languages do. Yeah, and if we want this to act like a number, we will need to add behavior to it. We need to add functions. Yeah. Okay. Right. Oh yeah, you can have empty structs. So that struct nothing that we had before, the built-in one, core.nothing. And we could make our own nothing, which is exactly the same in terms of its layout. It's not exactly the same in terms of a type, but in terms of type equality. But so yeah, this is just the layout of nothing. It's just a struct which is empty. This takes up 0 bytes, which is good. Unlike in C++, where you have an array of those things. I think if I remember, it takes up space. There's certain cases where things with no fields take up space, which is really irritating. Yeah, so so we can make one of these my nothings, and it looks like that. And the size of it is 0 bytes. That's good. And it has one possible value. Okay. Yeah, that's not too surprising, I suppose. Yeah.
It takes 0, but if you create a few variables of that, because they are a few variables, should they still somehow be registered or their address?
Yeah, great question. So yeah, it's such a good question. Thank you. So my nothing, so if we have A as my nothing and B as my nothing, so A and B are exactly the same in all ways, even though I made them separately. So this is what you get with structs. A struct is immutable. You can't change the value of its fields, and it doesn't have an identity of its own. So a lot of the time, the compiler will actually, if you use a struct, the compiler will take it apart when it generates code, and it won't ever allocate that struct anywhere. So that makes for super efficient code. Say you're doing maths with complex numbers, you don't want the compiler to have to allocate this aggregate struct every time. So a lot of the time it will just internally in the compiler, it just works with the fields. They go away.
So let's say you have a code and you reference A again and again, it's pretty much the compiler won't do anything with that. Yes.
If you reference A here, sorry, or?
Yeah.
Yeah, this one has no fields, so this will be compiled away, as long as type inference works. Now, if type inference doesn't work and the compiler doesn't know that this is of type my nothing, then it will it needs to allocate something to keep track of the type information. So yeah, so type inference is important for making all that work. But yeah, okay. Yeah, any other questions? Yeah.
Yeah, the constructor. Or the doubles is the type name.
Yes.
If you want to get that as a function instead of just as the type, there a way to do that.
Yeah, oh, that's a really good question. That's one I should know the answer to, and I'm not sure I do. I think the constructors are stored. The constructor for a type is kind of yeah, because my nothing is this is a data type. Whereas if you have a function, that's oh, okay, whatever. I'm getting off track here. That's a function. Anyway, I think I'm getting off track. Sorry, yeah, so can you consider the constructor as a function? It works like one. The type name works like a function. When you call the type name, you use it as a function. And you can make callable types as well. So you can make something that's a struct, which is callable. So you can use the brackets with it in a similar way. So yeah, there's a way of registering the call operator with types. And yeah, so that's kind of going on here. It's a little bit of a special case. So I think sort of no is the answer. They're not really distinct. It's not a separate thing, which is a function. Probably there will be somewhere down in the runtime, but I think at the surface level. But yeah, don't quote me on that one. So corner of the runtime that I don't fully understand. Okay, yeah, so we saw that, okay, so your question again, you asked a good question, which I've forgotten.
Although it is allocating zero space in memory for A, yeah.
Yes, you asked about A equals B, this one. So like RA and do I sort of like, is there an identity of the object which is separate from just its type, its fields?
Yeah.
Yes, okay. So for structs, the identity of the object is just its fields. You can't mutate the values inside of it, and the identity of it, like we have a thing called object ID, which is like kind of the identity of an object, is just like its fields. Oh, I'm not sure that's the perfect example, but we can see that these are the same. Yeah. This might not be what you want updated. Anyway, if the equals of the two things, that's just defined in terms of its fields for structs. But for mutable structs, these are things which are generally like allocated and somewhere in memory, and they have their own identity. So we could have this mutable complex 64 here. Or we could even have them, yeah, okay, let's go with this. Let's go with mutable struct, mutable. That's the terrible name. Okay, so this one's like, it's something which has no fields, but its identity is still distinct. So A is that A equal to B now? Well, no, it's not. These have their own address in memory, usually, unless the compiler could somehow prove like somewhere in a function that this is not relevant, then these have their own address, and they have their own identity. Yeah, so great question. Yeah, so the thing about mutable structs is you can change the values of their fields. That's generally why you'd want to use them. I suggest just don't use mutable structs unless you have to. Your code will be faster and more easy to understand if you don't use them. But sometimes you need them, so use them if you need them. Okay, generic structs. So we're halfway through. This is probably fine. Okay, so one more thing that we can do with structs is to create these generic, something like this generic struct. So say we want to talk about complex numbers. We know that they need to have like a real and imaginary part, but we might want the real and imaginary part to, like, and both parts need to have the same type, presumably. That's might be a good like assumption to make. But you could have complex values which are float 64 as their components, or maybe you could use big float as their components if you want to do extended precision work. So yeah, you can define this complex. I'm going to do this so I don't. This error here is because I think Julie got more strict about reassigning built-ins. There's already a built-in thing called complex, so we probably need to fix that one. So we can make a my complex. Actually, let us do this example here. Yeah, okay, so yeah, it's really useful to be able to make complex numbers with all different types. And we can define a function which works on any of our generic my complexes. So that's what this type annotation here is. We're saying like this abs2, this works on anything which is a my complex, and it doesn't really matter what the parameterized type T is that the fields are. So we can go abs2 of my complex. Oops. So we can do that. Or we could have one that's made of integers. So the type of my complex 1, 2 is this int 64 one, but this one is a float 64 one. Yeah, so you can really express very generic code, like very generic algorithms, and like over this set of possible complexes. Yes.
array.
Why don't we just use array for instead of this struct, you mean?
Yeah.
Okay. Oh, there's multiple reasons for that. So an array is in some sense a bit more like a mutable struct. Its slots are mutable. So you could use an array to represent a complex number. That would be vastly less efficient in Julia because that mutability implies a whole bunch of things that the compiler can't do, can't optimize. So that's one reason. Another reason is that you couldn't write this function here. Like you could, this part of it here it couldn't really be expressed. Like this is expressing that, like if you call abs2 with a complex, then this is the implementation. But like if you call abs2 with an array, I mean, like what does that actually mean? Like maybe it's not really, maybe you'd want to do this operation, it happens, but like you'd often like to like express different types of implementations for different things. So it's like quite meaningful that complex has its own like identity as a sort of concept. It's like its own noun in the world of that you're writing your program in. So really that's kind of the main reason, is that it's a distinct concept. So you would rather not use array for that. Sorry, I couldn't hear.
So the struct is meaning for the compiler and for the structure represent.
Oh, I mean, it's really both, isn't it? So I've kind of given you that, oh, it would be really slow. So that's for the compiler. Well, for the user too, people wouldn't like it if their complex arithmetic was about 100 times slower. So it's for the compiler and the speed of the language, but also it's for the abstractions and your expressivity of writing code, because the complex is like a different concept than an array. Array is like a very general kind of container of things. Whereas a complex number has very specific meaning. So yeah. Oh yes, and there's a little note here that yeah, that complex here, my complex is an abstract type. So like you have to put in a particular type int or whatever to make this into a concrete type. So that's a concrete type, but this is like a kind of a type constructor, if you will. You need to put in things into the slots to specify what the concrete type actually is. Yeah, so we'll talk more about abstract types later. Yeah, this little thing on type aliases, you can make a just like a shorthand for a type. So if you don't want to type complex float 64, then you could just type this thing here. Of course, this doesn't work because I called it something else. Oh, I've done, okay, so I've aliased the built-in one. That's not very helpful. Oh, whatever. What have I done? I don't even know what I'm doing. What has happened here? I'm not sure why that's a redefinition. I've done something funny here. Anyway, let's not worry about it. So yeah, you can just make an alias for things. So for instance, vector is an alias. Like that thing is a vector type of. It's an alias though for just a one-dimensional array. So this is a little oh, whatever. What am I doing? This one, sorry. Yeah, so you can have type aliases, all sorts of things. Okay. Yeah, so sometimes you've sort of written a generic implementation of something, but you get sick of typing the complicated version with like all the curly braces and everything. And so this is like a nice way to make that simpler. Okay, right, so tuples are sort of being grouped under struct in these notes, but I think, I mean, they're really kind of distinct in the type system. They behave a little bit differently in terms of things like whether something is sort of a super type of something else. But yeah, a tuple is just kind of, you can think of it like a lightweight struct where the fields aren't named. They just, they just have some values and you can index them. So this one, you can get the first value out of it. You can get the second value, which is true. You can get the third value. And the type of T is this thing, tuple int64 bool string. So one thing which makes these different from arrays is that each of these slots has a different concrete type. So if you return a tuple, or if you use a tuple in your program, type inference is able to grab onto like these heterogeneously typed things. And if you take out T of 1, then type inference will be able to figure out that that was actually an int if it's a tuple. But if you're using an array to like hold heterogeneous things like that, then it would not be able to figure that out because there's only one type parameter for array. So like if we did this one, we could also do this, but this is a vector of any. So the compilers realized that these things here don't really share anything in common. So the only way to make an array out of those is to have any as the type. And as I said before, that's the superset of all types. Okay. Yes, you could do that thing. So sometimes it decides. Oh, can't type. So we could do this. So this is a way of specifying like a particular type. The syntax, that's really confusing syntax. Sorry, as an introduction to this syntax, but like this says it's an array of any. So I could make an array of any with like integers in it. It's now an array of any. This is less efficient, but both the integers are still stored. And in the same way, I can make an array of these as union here. And that actually might be what you want in some cases. This might result in better code because type inference will be able to figure out that when you pull the first thing out, it's one of those possible three, which could be quite useful, but it won't know that's integer. As opposed to a tuple where you pull out the first value, it knows it's an integer in this case. Okay, so they're a bit different from arrays. They're also immutable. So you can't change the values. You can't go T of 1 equals 100. What am I doing? I've already made it. I made an array out of it before. So if we go back to the tuple version, you can't set the first value of the tuple. It's immutable, just like these structs up here are immutable. Although I didn't show you this actually, I think I skipped over it. But yeah, you can set the value, the field of a struct like that if it's immutable. Yes.
What happens if you make a method like
Yeah. So you can for your own user-defined types, you can make methods of set index. But we couldn't implement set index for a tuple because there's no kind of like primitive thing to set the index. Like set index is kind of the definition of how you would set the index. But there isn't like tuple is a built-in type. And there just isn't something to set. There's no like built-in function to set like that index. So we wouldn't be able to implement it. Oh, so let's make a bogus implementation. I like this. We can implement it. It's just we can't actually set it. We can't fulfill the contract of set index. So it's saying that it wants set index with this tuple type. Like, so let's actually implement that. Oh, whoops. X is a tuple. Whoops, got too many columns there. So we could try and implement that. Oh, which way around is it? I forget which one. Anyway, it doesn't matter. So we're just going to go function that. And then, so we can do a thing like print one. This is very evil. Whatever. I forget the emoji. Anyway, that's fine. I was trying to write an emoji. Okay, so like now we can do this. However, it didn't like do anything. Like, and we can't do that. We can't actually fulfill the contract of set index because there's no like fundamental like primitive which we could use to set the index of a tuple. As opposed to array, where there's like this fundamental built-in thing, like a built-in function. I forget what it's even called. I don't think it's set index. I think there might be something else that it uses. Maybe it's just set index actually. Anyway, let's not digress too far. Anyway, arrays have that fundamental thing built into the runtime, so you can implement set index for them. Okay, so we've gone over generic structs, gone over type aliases, gone over tuples. Oh, there's also name tuples. These are very useful if you kind of want to have a tuple, like you kind of want a struct, but you're only using it like in one little place in your program. And you just don't really want to write separate struct definition somewhere, but you do want to be able to use named fields for something. Then you can make a named tuple, and that's the syntax for that. So it pretty much acts exactly the same as a tuple in most ways, except that you can access the fields with the names of the fields. So yeah, that's pretty useful. Okay, we're up to arrays, which we've already seen. Whoops. Yeah, so arrays, I don't know what to say. So they can be multidimensional. You can have array literals like this. Whoops. Oh, I can't type. So this is a matrix or a two-dimensional array. The one-dimensional array you've already seen. You can have higher dimensional arrays if I can get the syntax right. I forget if it's that, or we'll find out in a minute. No, I got it wrong. Anyway, that you can add more semicolons to like separate the dimensions of arrays if you want to. Yeah, I've done something wrong with the way I've constructed that. Anyway, whatever. It's probably like I needed to put this dimension and then that. Yeah, no, it's not. Anyway, go and look up multidimensional array syntax if you wanted to construct high dimensional arrays. Yeah, so what are arrays for? Well, they're kind of a heterogeneous but like mutable, like they're homogeneous, sorry, a collection of values which you can access by their index. And we've already seen that you can have arrays of abstract types, like array of any. So you can just hold whatever you want in them, and you can access by index. You'll find that you always get more efficient code, though, if you have arrays of concrete types. And that's because the compiler can lay the data out much more efficiently that way. Yeah, so they're mutable. You can edit them. You can add values to the end of them. So this is something that's very useful. So if you have an array, you often want to add to the end. Use the push function for that. And now you have an array with something like that on the end. And likewise, you can remove things or you can add them to the front. Push first. So we keep making our array bigger. So yeah, it's very useful, especially mainly with vector actually, to be able to add and remove things from the arrays. And you can mutate values, whatever, So yeah, yeah, the element type of an array is accessible via L type, and it knows this one is element type of int, or int64, which is an alias. Int's an alias for that. Okay. Oh, and there's these convenient like aliases for vector and matrix. They're just arrays, 1, 2 dimensions. And you'll find that like if you're writing mathematical algorithms, like pretty much like most complicated data structures will be expressed in terms of a set of arrays which index each other or those kinds of things. Okay, so final one, strings. Oh, and I mentioned before, Julia's actually changed a little bit since these notes were written. Array is no longer a like primitive built-in type. There's this new thing called memory. That's like kind of a low-level detail, but so like these aren't the kind of primitive built-in thing anymore. But yeah, for your purposes, they kind of are. Okay, strings. These are kind of like an immutable array of uint8 code points. So they encode UTF-8 data. So we can have a string with like, is it smile? Yeah, smile. So we can have a string with emojis in it because Julia supports all of Unicode. And code units. I think it's code units. Yeah. So then you can like go and look at what's actually stored inside there. There's a code units function, and that's that'll let you look at the underlying UTF-8 data of this string. But yeah, it's just a certain way of encoding like any character which the Unicode consortium have like deemed worthwhile to have. So the smiley face takes 4 bytes. Most things that we would write in Latin letters just take 1 byte for every character. Okay. Yeah, there's just a note here about there's other types. There's a whole lot of types in Julia's base library. Things like set and dictionary are implemented, but they're implemented like they're not primitive. They're just implemented in terms of structs. Or some of them are primitive types like floats. So you basically put these other types together as fields to make like more complicated abstractions like dictionaries or sets. Okay, so, well, we're nearly at the end. Not gotten very far. Yeah, so like the first, we'll get into this a little bit. The first bit of this was sort of like, these are the kinds of ways you can express types. The next bit is sort of, let's look at how you can express logic and functions. So we've looked at a bit at the nouns you can have, and we're going to look at the verbs. What can you do with things? So I am going to skip over that. I think we've kind of looked at a lot about this kind of thing, but we will look at this. So code typed is a very useful tool, which will let you see what like type inference is actually doing with an expression. And yeah, the compiler contains a proof engine, or like it's a way of propagating type information through the program, which can figure out like what is the type of some intermediate result, and it uses that to generate fast code. If it can't figure it out, it'll just degrade that type to something more general, like maybe any. It's pretty keen on degrading to any if like it can't figure it out, just to avoid having really complicated unions and things. And yeah, so the code still works if it can't figure it out. It just will be slower. So we're gonna see like we'll use code typed a bit to kind of explore some things here. So if else, I think you will have seen this. If you've written any significant amount of Julia code, you must have seen this already. But there's one little interesting thing here, which is expressed in this little code block. So if we have x42, so we're saying before that every expression has a value. So even an if-else block has a value. So we can assign this result of this whole block to this thing x is even, and it's going to be like a string to say whether it's even or odd. So in this case, x is x even. It's a string. Yep, 42 is even. So what's going on here is that the first, like this block, the last thing in this block is the value that's coming out from this side of the if, or the last thing in this block if it went in that side. So there's only one thing in this block. And this is a little bit of an oddity if you're not used to languages which are more functional, I suppose. But it kind of unifies like this block syntax with other languages have this as a sort of ternary expression, it would be called in C. Excuse me. And this is the C way of doing the same thing, like this kind of syntax. If X is even, then you go in this bit and you produce that value. Otherwise, you produce this value. And in Julia, both these things are exactly identical. This one is just a syntax sugar, we call it, for this one over here. It's just a like more expressive, like shorter kind of way syntax sugar is for writing the same kind of thing. Right, so now let's get to this abstract type, which we've seen already, because someone asked a good question. So if we did this instead, if it's even, then we return the Boolean true, otherwise return the string false. Okay, well, that's fine. It's weird. It doesn't, like, it might not be useful, but yes, it works. But if we look at the code typed, we see something interesting. So this is what is the computer, like, what is the compiler able to figure out? So it's able to figure out that, well, there's a bunch of implementation stuff that it's done, but like the actual return type here, you can see is a union of Boolean and string. So yeah, type inference is able to figure out that it could be a bool, it could be a string, and in this case, it wasn't keen to degrade that to an any. So that's nice. It will generate like more efficient code. So yeah, it's an abstract type. You can't make a value of this. You can make like you can make a bool, you can make a string. Those are the concrete types, but you can't make a value of this union. Okay. Yeah, so I'll just go through like one or two more things and then we're done. Just gonna go till 7. Okay, shortcutting logic. Julia has it has normal Boolean operations. So you could use the ampersand for logical and the pipe for logical or. That's sort of a pretty common choice, I guess, that syntax for various languages. Now, the single ampersand will evaluate both sides of this. Whereas, so these ones you won't use as much. What you'll probably use in practice is the double ampersand and the double or, the double bar. So that's a shortcutting operation. So if we have something more complicated than just a literal in this first side, so like we have some function we need to compute, then if this one turns out false, we don't actually need to compute the second part, because we know that this is already false, and whatever false or true is always false. So we don't really need to compute the second part. So that's what you would use X and Y for. So that's actually equivalent to this code. And the compiler will, in fact, simplify this down to this code. So if X is true, then it needs to compute Y. So that's what that does. And if X is not true, then it's just the false value. There are sometimes that people kind of abuse this. I don't know, it's either an abuse or like a kind of pretty kind of shorthand, depending on your point of view. So you can do this kind of thing. So X is 42. If X is -1. So yeah, if you have something on the right-hand side which causes a side effect, then you can use this syntax to sort of have a really short way of writing an if statement. I don't personally love this, have mixed feelings about it, but a lot of people do use that. So just to be aware that like if you see this kind of thing, that's what that's all about. Yeah, so this one I do find a little bit nicer. So it just reads nicely in English. If X is greater than or equal to 0, or X is greater than or equal to 0, or it's an error. So I think that kind of reads nicely. And sometimes I use it, but you know, it's a bit odd. It's a bit odd to look at. Yeah. Okay, I think we're basically done. It's 7 o'clock, so we will have to continue with blocks of code next time. But yeah, thanks for listening. Yeah. Any more questions before you leave? Oh, everybody. Oh, great. That's excellent. Yes.
How to like define with 4 different variable types? Would that just
Tuple, like this kind of thing, or I'm not sure. Like that kind of thing, or yeah, that's a tuple. Yeah, so you can have any number of things in a tuple. Yeah. Yes.
It's like, for example, I was messing around in front of a string and the record didn't let me.
And you sorry, I couldn't hear.
The record wouldn't let me make a complex string, so there's clearly something that stops that from happening.
A complex string. A string of, I don't understand what syntax you're after.
Complex, curly brackets.
Oh, yeah, okay. Oh.
Yeah. Complaints when I-
Yeah, there you go. Yeah, it's telling you exactly what the issue is. Yeah. So when there's a little lie in here, it's like the struct definition of my complex. It's not actually this. It's like it's this thing. Oh, how do we write this even? I've actually forgotten. Haven't used this for so long. Something like this. I don't know. I've written it wrong. I've written it wrong, but yeah, there's a bound. It's like what possible types are bounded. It's probably just in here, actually. Let's go. I forget the syntax. Yeah, there. I haven't written this for ages. Yeah. Yeah, so now we can't make my complex two with like a string. It's not even allowed to make the type. Yeah. Yeah, it's a good question. Yeah.
Is tuple like kind of constant array? So you cannot change the value.
It's sort of like an immutable array. Yeah, except that it's not quite the same. As I was saying, like each of the slots can have their own concrete type, and the compiler knows all of those.
Yeah.
So like vector of int, there's only one type I could put in there, but tuple I can put int, bool, string. So that's a tuple with 3 things in it, exactly 3, and they're different types. So the type has a way of putting the information in.
Can you have multi-dimensional tuple?
No, you can't have that.
What's the difference between struct and type?
Between a struct and a type. I mean, a struct is a certain type of type. They're different things. I don't think I understand the question very well.
Yourself, and you can define type yourself. I don't think it's the difference.
You can define a type yourself, or
Can we?
yeah, I mean the definition of a struct is a type. That is a type in Julia. I don't think I'm quite understanding the question. So there's no type keyword. That's not a thing. If that's what you're asking, that's just not a thing.
Okay, so we can
Yeah.
only define a struct, not type.
Well, a struct is a type. There's just no keyword called type.
Differently defined.
Or the data type that underlies these things, I don't think I quite understand. But like, yeah, the type is not a keyword. There's no thing.
We are not supposed to define.
No, you do define types. Struct, when you say struct
Yeah,
such and
I
such
mean-
end, that's a type.
Yeah, I mean.
Yeah.
Strictly a type, you just. Is,
Oh, yeah, no worries. Yeah, I don't know.
Because type and struct are not the same.
Well, a struct is a constructor of a type, like it makes a type.
Yeah, it makes a type. Yeah, struct makes a type. There's also ways of making abstract types. I mean the tuple constructor that we've got here. That's it's gone out of the back. It's gone out of the buffer. But yeah, this thing. That is a way of creating a type.
Is type kind of set?
You can think of a type.
Set of all values.
Yeah, you can think of it as a set of all values. Like the compiler doesn't represent it that way because it would run out of memory. And some types have a like unbounded set of values as well. Like an array, for instance, like a vector that has a number of slots. So it has an unbounded number of possible values.
About a struct, how do we define a struct of odd number? If we want to do something like that. Because
Yeah.
it's kind of a subset of type and it's not kind of building up from other types.
Yeah, so like what you probably do would be you define I mean, you could use a primitive type and you would just have to constrain the bit representation, or you'd have to use the bit representation in a way which is like, oh, where, like, let's say you had actually one way of doing it would be this, struct, even number. So we could have like this. So if we store only the half of it, we can have any number in there in that slot, and it will be, when we multiply it by 2, we get a valid even number. So it's like one possible way of representing it. But then you need to add the semantics yourself, like you need to define what it means to show an even number. So we could actually do that, base.show.
So because we only define the struct, but we did not define other operations with the struct, so it's not useful at all at this point.
Yeah, it's not useful, but like we could do this. So we can start adding functionality to this. So we'd go print io 2 times n dot rfi, like so. And then if we go even number, show even number 2, like 1. Oh, now this is like really weird because we need to make the constructor ourselves as well, because like you don't want to put a 1 in and then that actually be so this is going to be funny. So even number of, yeah, okay, so we need to go.
So, if I want to do something like a struct of prime numbers, is
Oh, we need an inner constructor.
just I define something myself, not using struct.
I mean, you can use struct. Struct is fine. You just need to define the functionality around it to make it represent that thing. Yeah.
And
Struct is what you normally want to use.
because the type of type is data type, it's kind of self-referential, and that is some paradox around that.
It's not a paradox, but it is a type that you can't write in Julia, and it's built into the runtime. Yeah, it's not a paradox. It all works. It's just that it's self-referential. Yes, it is.
And what is the type system? I see it a lot in a lot of places.
Yeah, last question. I want to get to you guys' questions so you can have a chance. What is the type? What is a type system? Yeah, good question. Like I guess for Julia, it's the whole kind of thing around how so like the kind of algebra, I guess, of types. So you can have you can join types together, like with the union. You can intersect types. So you could type intersect bool and string. This is the union of nothing. There is no values of that thing. So yeah, it's kind of an algebra, I guess, in a sense. And I don't know, the type theory people have a lot to say about what a type system is. I don't have a great answer to that one. Yeah, great questions. Can I get you to ask the questions though, so you have a chance?
If you could figure out a way to like hack it so that you could change immutable elements, would you basically be like making all immutable things mutable? Like would you lose the benefits of?
So yeah, how do you mean hack it?
If you could implement the
like set index, like that we were trying to do before. I mean, that would be changing the Julia runtime. So you like go to the C code and you start changing it. And then of course you could change the meanings of things. But yeah, not from the Julia level, you certainly can't. Like there's no built-in thing that would allow you to implement those basic operations. And also the compiler itself is a really big pile of code, which makes a whole lot of assumptions about the struct is immutable. It makes those assumptions in many, many places across the whole code base. So you'd need to go to all those places and say, no, it's actually mutable, because otherwise you break all of the invariants that the compiler's assuming, and everything will crash. Yeah. So like while you can maybe like in certain cases, like you could say figure out where the fields of an immutable thing were stored and then like find a pointer to them somehow and like set them to something else. Like that's outside the semantics of valid Julia code. So like anything could kind of happen. You might end up with seg faults. You might end up with nothing weird happening. It might just sort of seem to work, but then other times it doesn't work. So yeah, you can break the language's semantics sometimes if you like do naughty things, and then the whole system explodes. Yeah, yeah. Yeah. Rose, yeah, nice to meet you.
Goodbye.
See ya. See you next time.
Kind of answered my own question in the end a bit, but with the double ampersand,
Yeah.
with it being like syntax sugar instead of an operator. So I was trying to do like type of double ampersand. It says that's not a.
Ah, yes. Yeah,
so
yeah,
it's
yeah.
that kind of weird, but then
Ah, yeah.
then I was thinking, oh, I guess in Julia, if you were passing it to like map or something, you just use the single ampersand because shortcut doesn't mean something. I just found it kind of like funny. That
Yeah, it is funny.
like a built-in.
Yeah, because a double ampersand is not a function. It's
Yeah.
special syntax. It doesn't like when you have a function call, you need to evaluate the arguments to the function,
Yeah.
right? Like so there can be no sense in which double ampersand can be a function.
Yeah.
So the right-hand side would never be evaluated.
Yeah, it's not
Yeah.
like Haskell. Like in Swift, I think the double ampersand you can implement it, but they've got another feature where you can have an argument that's marked as an auto closure, and then your
Oh.
argument becomes like it's a lambda instead.
Uh-huh. Yeah,
And
yeah,
then, so
yeah.
you give it these two expressions, and the right-hand one becomes like a lambda under the hood, and then the function gets that, and then the function can like evaluate it.
Yes, yes, I
So
see.
it's like,
Yeah.
it's
Yeah,
like-
so I think like in some sense, the equivalent thing in Julia would be like macros and like
yeah,
code
I guess that-
generation.
yeah, true,
Because
true.
this thing is allowed, like we can have this. So I'm still recording, I'm causing problems for Yoni, but anyway, he'll cut the end off, I assume. So like this is funny. Have you seen like expressions as data before? So
Julia.
let me, yeah, what have you seen them in?
Well, I guess like not as data in the data sense, but like macros in Rust and Swift, I guess, allow you to do similar things.
Right, yeah, no, totally.
Yeah.
Yeah.
Not quite. It's actual data in your program.
Yeah, because like Rust will do like the macro expansion. It does have syntax as data, but it's only visible during like macro expansion, which is like
Yeah.
a separate pass. Whereas Julia, everything is in the same
Syntax
runtime.
tree.
Yeah, like so actually what Rust will do is give you like a token stream and then you can
Yeah.
construct a syntax tree out of it, which is like an interesting choice, but it's
Yeah.
got its benefits, for sure. What Julia does is if you have quoted syntax like this,
So that's the quoted.
yeah, this is,
user
yeah,
syntax.
this is what this like frowny face operator is. That's not, it's not actually, it's actually a colon with something after it. So that thing there is the quoted version of
Ah,
A.
okay.
Well,
And so the colon is a quote. It means this thing coming next is syntax. It's not values. So so this thing here is actually a tree. We can look at it.
Okay.
So yeah, and it knows like obviously the rules of operation. It knows that times is more important than plus. So this bit here is grouped in the tree like that. And the plus is like there's like, well, these are both calls as well. They're calls to functions. The name of the function is plus and the arguments are A and then this other thing. And then this bit here is a call to the times function with the arguments B and C. So yeah,
Okay, so then does a macro kind of like gets given quoted syntax? and then, like,
absolutely it does. Yes, it does. Yeah, so show.
The output of the macro is output an expression and then Julia evaluates that.
Yes, yes, you've got it. You've absolutely got it. Yeah, yeah, yeah. So we can write one if you want. Like we're gonna write a foo macro. So like this expression EX is gotta be, well, it can be anything. So like we're gonna produce some quoted syntax out of that. Actually, let's write the function version of this. We're just going to write a function which does it. First of all, anyway, so it's going to be print line, and then we want to stringify this. So stir equals string x. So we just make a string representation of that expression, and then we interpolate that into here. So this is sort of like the dollars is an escape. It lets us put the value into this expression, this quoted expression. Yeah, yeah. And then we want to put in this, although I've slightly done a naughty thing and not escaped it. We would need to write that, but let's just ignore that for the moment. So, okay, so foo of, 1 + 2 × 3. This produces some syntax, right? So it's made this string, actually, I got it wrong as well. So we want this to be equals something. Like this is like, say, a show macro.
Yeah.
So yeah, it's going to say this is what the expression was passed, but it was a string, so that's fine. Just this bit's done when the macro expands. It's converted to a string. Then we've got these other bits, and this is the value, not the string. Like it's the value of the expression. So yeah, that's basically what you're doing when you're writing a macro. Is you're just doing that. So we turn that to a macro, and then we can go at foo. And then we can get that out of it.
And then I assume like to evaluate the quoted syntax, can like call it or?
Well, you can see that I've just pasted it in here.
Yeah, so then your function foo outputted the quoted.
Yeah.
syntax.
Oh, yeah. Not sure what you're asking.
Like, because it's outputted the quoted thing, but then it hasn't like run it. So if you wanted to emulate what the macro has done, where it actually put it in.
Oh, yes, of course. Yeah, okay, so we can do that. So we can go foo. So this produced the syntax, and then if we want to evaluate that, we can use eval.
Okay, eval.
And there you go. So that eval will just evaluate any syntax you give it.
Macros.
Yeah.
Like,
you can. So one other thing, you can also see what this thing is going to be. Oh, where has it gone to? The scroll back buffer is broken. So there's a little tool, macro expand, which will help you with seeing what the syntax is.
Yeah.
So you can do that. Sorry, what was your question?
I think in Rust and Swift, they're the macro ones I've had experience with, and they like put a big emphasis on like, well, in Swift at least on like hygiene, so you can't just make up a new like symbol and then like hope it exists.
Yeah. Yeah, so Julia has answers to those things. So strictly speaking, as I said before, as I mentioned, I should have put ESC here. So that's because if I use some symbols in here, they're attributed to the macro context. So like if I go, oh my goodness, what's happened? What on earth? Oh, okay. Oh, well, demo's over because I ran out of battery. That's something to learn.
Okay, so it's like kind of keeps track of that, and then
It's probably a good sign that I should leave, but yeah, happy to keep chatting though.
if you called like a macro, if your macro calls a function that doesn't exist, I mean, like in the quoted syntax, it has a call to a function that doesn't exist. Does it just do that?